sudden hitch, an electric twitch. Sometimes I swear this body's got a mind of its own. This is the naked truth. This is the light. There's only one place left to go. Shiny cloak and an unseen silver dagger. You can talk till you wake. Give yourself one more break. You can tell by the look on his face that it just doesn't matter. 'Cause this is the naked truth, and this is the light. There's only one place left to go. What I'm saying, though I hear what you say. Think with a dagger and you'll die on your knees, begging for mercy, singing please, Mr. Please. 'Cause this is the naked truth, and this is the light, and there's only one place left to go.
FXCC welcomes you to the live webinar on lead-free solder development towards green technology. You have joined the webinar on lead-free solder development towards green technology. You are welcome. Kindly stay online. The webinar will start shortly. With the outbreak of COVID-19 pandemic, ensuring that education is not obstructed during this unprecedented times and lockdown, Francis Xavier Engineering College has been in the forefront in organizing various events with the aim to upscale the skill sets of the students and faculty through various virtual platforms. Among other events, considering webinars would serve the purpose during these times, expertise in the relevant field are looped in to present webinars on the recent trends of technology. Kindly stay online. The webinar will start shortly. FXCC welcomes you to the live webinar on lead-free solder development towards green technology. You have joined the webinar on lead-free solder development towards green technology. You are welcome. Kindly stay online. The webinar will start shortly. With the outbreak of COVID-19 pandemic, ensuring that education is not obstructed during this unprecedented times and lockdown, Francis Xavier Engineering College has been in the forefront in organizing various events with the aim to upscale the skill sets of the students and faculty through various virtual platforms. Among other events, considering webinars would serve the purpose during these times, expertise in the relevant field are looped in to present webinars on the recent trends of technology. Kindly stay online. The webinar will start shortly.
Francis Xavier Engineering College, Vanarpete, Tirunelveli.
Good morning, one and all. It's my pleasure and privilege to welcome you all for today's webinar session. First and foremost, let's invoke God's grace and blessings so that He guides throughout our knowledge endeavor. On this occasion, I am extremely happy to render a warm welcome to our guest speaker, Mr. Amaresh Singh, a lecturer and researcher working at Sigi University, Malaysia, who will share with us his expertise and experience on lead-free solder development towards green technology. I welcome you, sir. I also welcome all the participants, learned professors and students from various other colleges who have joined us today. Once again, on behalf of Management and Department of English of Francis Xavier Engineering College, I welcome you all and wish you have a great time ahead. Thank you.
A very good morning to one and all present here. I deem it a great honor to introduce to you the speaker of this webinar. Mr. Amaresh Singh, lecturer and researcher, is a faculty of engineering, built environment and information technology under the mechanical department, Sigi University, Malaysia. He received his bachelor's degree in mechanical engineering from Multimedia University in 2012 and master's in science in the year 2015. He has submitted his PhD project and awaiting for the vivos. He has 2 years of industrial attachment in Daking Research and Development Center. He has been doing projects on foam compression to investigate the experimental and simulation correlation. He obtained Chartered Engineer title from IMechE UK in the year 2019. His research area of interest is in the field of soldering and surface mount technology. The studies are mainly done for the low temperature soldering and currently he is focusing on nanoparticles reinforcement. He has also published few articles in reputed journals in this field. An internal grant under the same research area is still under process. Sir, we are privileged to have such an eminent personality as a speaker for this webinar. Over to the speaker. Thank you.
Having me. I'm Mr. Amresh Singh, and enough introduction is given by our fellow researchers over there. I'm actually currently instated in Segi University, but I'm also having some collaboration with my other universities and my previous universities. So again, I would like to adhere my thankful to Francis Xavier Engineering College for having me here. So as mentioned, today I'll be talking about the lead-free solder development towards the green technology. So without the further ado, I'll just go into the topic of today. So I'll just give a brief introduction. I mean, this is the content. I'll be first explaining on the field of research, background of research, what are the problem statement in this particular topic. I'll also give a whole idea in terms of literature review and some of my current works that I've been doing, and also the future works, and of course I have to cite some references. So looking into the field of study, I'm mainly investigating the solder alloy in an electronic packaging industry. Just bear with me, I'll actually explain what is solder alloy and what are the types of solders that have been used in this current industry. So then I'm actually incorporating nanoparticles additions on solder alloy. Some would argue, why is it needed that the nanoparticles inside the solder alloy? Again, with the literature review and also my current work, I'll actually explain what goes on when we add these nanoparticles to the solder alloy. So we have to, obviously every achievement or every objective has to be dated or has to be satisfying a certain properties. So we will be looking into a crucial properties, not I mean many crucial properties upon these additions of nanoparticles in a certain solder alloy. So this background of study basically involves nanoparticles additions because nanoparticles are small in scale and they also satisfy the trend towards miniaturization. As we can see, our gadgets, mobile phones, our televisions, laptops are not growing big in size, but they're actually reducing in size. But then how could it be hold in terms of a long-term usage? We know our mobile phone has packaging chips inside that has to be held by a certain medium, which is the solder alloy. But looking at its size, is growing, I mean, it's getting smaller. So we need to do something to this particular solder alloy. It should be physically, microstructurally, and mechanically stable. So we will be looking into these particular studies. So problem statement, as you guys have seen my title, the title for today is lead free. Okay, lead free means we are trying to avoid plumbum, right? We are trying to avoid plumbum because plumbum is categorized among the 20 or within the 10 most hazardous elements. So we need to avoid or reduce the usage of it. But then looking at the particular current of most used solder is basically the plumbum solder. Plumbum is being mixed with a tin and then they produce the lead solder, which is thin plumbum. It is known to have a very good properties in terms of mechanical. It is also having a low melting temperature. The temperature is only about 183 degrees Celsius, which means it during soldering process it would not damage the other components. For example, the LEDs or transistors, it would not be damaged. So being this proficient, to replace this solder, it's quite a challenge because not many industry would want to accept a new solder that is probably expensive, at the same time not giving improvement. At the same time, as I mentioned earlier, nowadays gadgets are getting smaller. So what I've looked into a particular solder is the lead free SNBI. I could say lead free because now tin is SN here. Tin is being mixed with a bismuth, Bi, rather than a plumbum. Of course, there are many other solder that has been studied as I will be going through later in the literature review. So in this particular current work that I'll be talking later, I'll be using lead-free SNBI solder. All right, but then it said that it has a mechanical strength which is not that good. So that is why nanoparticles are being added. So in terms of mechanical properties, it's also crucial that the nanoparticles addition tally up or actually satisfy a high mechanical properties. We'll be looking into hardness and also shear strength. I'm aware that most of us know what is hardness and a shear strength of a material is. So basically, when we are dealing with the mechanical properties, we have to look into what is happening inside the solder when it's being soldered on a substrate. Substrate means it's a platform, or in another case, it's a printed circuit board that where the solder is being melted and the components are being attached. So there would be a formation of a certain compound which we call by intermetallic compounds between the solder and substrate. So like we can see here, the properties of the solder will influence the bonding between the solder and substrates. So let me just go into what are the research that has been done. Not mine, but we have to gather some literature review and give a certain introduction so that we know what is going on in this current soldering technology. As I said earlier, we can see here these are PCB boards. PCB boards are printed circuit boards. There has been a platform that devices are attached using a medium, and this medium, as I've labeled there, is the solder alloy, or in this case it's a wire. So what are we trying to do here is to replace the traditional lead solder SNPB to a new lead free solder. That is our main objective. As long as we can eliminate the plumbum from the SN solder by addition of other materials, we are actually producing a lead free solder alloy. But what should it do? Okay, lead-free solder alloy, when it's being soldered, it should be providing a metallurgical effect. That means when there is a heat applied to the solder, there would be a metallurgical joining method because we are using the solder. So by this means, the chips are connected. Chips here means the electronic devices are connected through the soldering. We can see a word here that says wetting. Wetting basically is the ability of the solder to spread on the substrate. It's very important that we will be looking into a wetting aspect later as well. And as I again mentioned, metallurgical bond will be formed between the solder and substrate. So we know this is towards the surface mount technology because we are not doing anything to the PCB board, but we are actually doing it on the PCB board. We are not altering the PCB board. So it's actually a surface mounting technology. So it should provide electrical thermal in sense of course, it should be meltable, or it should be having a melting properties, and mechanical continuity is in terms of the shear strength and also hardness. As for the electrical, of course, it will be conductive because we are dealing with metal elements, right? So there's no problem in electrical as long as we are using a conductive electric element. So I'll be looking into a certain types of lead-free solder alloy. But before that, I've introduced slightly about the lead solder, which is having said to be the best candidate so far, but it's actually a lead solder. It has a low melting properties, which is good because it does not damage other components. At the same time, it does not need any soldering adjustment. The temperature no need to be adjusted because usually the soldering temperature is less than 250. Good mechanical properties. It's also low cost because it's very much available. Of course, it produces good interfacial bonding. Other lead-free solders that being studied are such as tin zinc SNZN, tin argentum SNAG, tin copper, tin argentum copper, tin zinc bismuth, and tin indium. I've listed what are the drawbacks of this particular lead-free. They are lead-free, but I can see that these have a certain problem. For example, let's take a three element which is SNAGCU. This is the most studied currently. This is the most studied solder currently, but it has a high melting temperature of 217 degrees Celsius. That is around 20 degrees near to the expected soldering temperature. So there might be a problem during the soldering process. At the same time, only producing lead-free solder is having a high mass. So let's say if we want to use a low melting temperature solder, but then we need to increase the mechanical properties, we can't just add another element because we're actually reducing the size. So we are looking towards the miniaturization or addition of nanoparticles inside the solder alloy. There are few methods that have been studied to be used as a nanoparticles addition. So first one is chemical reduction. That means they will be using a certain chemical amount, chemical component to reduce or to break down the bulk solder to nanoparticles. But then this is again hazardous and it requires chemists to do this problem. All right, we are actually engineers, so we try to use another method, which is consumable direct current arc method. But this is a very high advanced method that we need a certain equipment which is quite expensive. Then we come to the conventional way of mechanical mixing method. I'll be explaining this method later. It's basically intentionally putting in or dispersing the nanoparticles into the solder alloy. So of course, being said as nanoparticles, the scale must be in nanometers, because even if the particles are in micro scale, the influence that they impart to the solder alloy is different when they are being nano scale. So it's very important to make sure the particles are in terms of nano scale. So this will be the main properties that should be achieved by a lead-free nanoparticles added solder alloy. It should be possessing low melting temperature, good wettability. There are certain aspects in terms of wettability. We'll be looking into that. A satisfying, or let's say an excellent microstructural properties. How do we evaluate this? It seems like more subjective than rather analytical, but I have a method. I've also studied a result that will show how we can relate the microstructural properties to the mechanical properties, which is again the hardness and also the shear strength. Okay, hardness is the ability of the solder to resist deformation, because we know our mobile phone, for example, we might drop it, so it should have a good impact. All right, so hardness and shear strength is a crucial mechanical properties. So these are few studies that I've gathered. People have done these few studies, and we can see certain nanoparticles are added to a certain solder alloy. So we can see, okay, let me just give you a highlight that beside the solder alloy, it's the initial melting temperature nanoparticles. We can see that some of the nanoparticles have increased the melting temperature, but some of it has reduced the melting temperature. But what is more important here is the increase and the decrease is very minimal. So there's no need for the alteration to the soldering temperature. If our soldering temperature is less than 250 degrees, it's okay. It's okay to use the nanoparticles because it's not elevating the melting temperature. At the same time, it would not cause any damage to the other components. So this is the important results that we see. But why is it happening? So let's look at the decrease of the melting temperature first. Nanoparticles, when we add them, they actually increase the surface stability of the solder alloy. That means the solder alloy will lose its energy earlier without the nanoparticles additions. Therefore, the decrease happens. Whereas the increase in the melting temperature is because of the local dissolution of the nanoparticles in the solder alloy. For example, when we are melting the solder and we are adding the nanoparticles will tend to have, of course, a higher melting temperature. So they actually produce a local dissolutions. So it slightly increases the melting temperature of the solder alloy. But not to worry, this actually gives us a good idea that addition of nanoparticles is not eventually changing the melting temperature drastically. It's an important aspect to look into. As another second part of properties is the wettability. We can actually separate the wettability into few parameters that I've concluded here is contact angle. In my work, I've also studied the spreading area and the spreading ratio. But before that, let's look at the contact angle. A lower contact angle, as you can see at the lower slide, means a good wetting, because if you're having a higher contact angle, it's a bad wetting, means that it can easily chip off from the printed circuit board. So let's see what happens when we add nanoparticles. Here we could see that a small additions of nanoparticles, for example, we add 5% of argentum, it tends to reduce the contact angle to 32 from 38. But then when we add 5% of zirconia, it seems to increase the contact angle further. So here the weight percentage actually plays a part, because when we try to add more nanoparticles have a certain character that they will attract to each other if they are a lot. So when they are trying to attract to each other, and during the melting process, at the most end of the solder, at the edge of the solder is where the high energy is being present. So these nanoparticles will be at the high energy area, and if the additions are a lot, they tend to agglomerate. So what happens when they agglomerate, when they gather together, that means the solder will not be easily spread. There's like an impeding motion or impeding item or particles that will not allow the solder to spread properly. So here it's important to keep the weight percentage or the addition as low as we can, because even a small amount of nanoparticles additions can actually increase the other properties such as mechanical. We don't need a lot. Whereas it's different when you're trying to add in elements, a bulk element. If you add in a small amount of bulk element, it does not give any significant improvement. So let's go to the next part. Right, microstructure actually produced when there is a melting point and there is a diffusion between certain elements. So this is basically a metallurgical part. So I would not want to go in depth because it involves more towards material science. You have to look into the energy of a certain element. Let me just give a brief idea what happens. You can see that in a certain picture of A, B, and C and D, you can see like a pattern, right? You can see like a pattern. So let's take it as an island. You can see that the island grows when the nanoparticles are added. These islands are known as eutectic area. Eutectic area is a point where you have many compounds. For example, you have argentum and tin and the nanoparticles at the eutectic area. The eutectic area will have more than one compound and also combinations of compounds, intermetallic compounds. These intermetallic compounds are important to actually resist deformation. So when I say resist deformation, it basically helps us on the hardness properties. This can be only achieved if you are adding small nanoparticles. If you are adding large sized microparticles, you would not produce a eutectic area because these microparticles will not act as a grain size reduction. So we can see in the third bullet, I've said grain size reduction. This grain size reduction happens when the nanoparticles are in small scale. What happens is that when the element tries to grow, these nanoparticles will impede from the growing of the element. So basically, before the nanoparticles can grow, before the elements can grow, solidification already happened. So the solders will be solidified even before growing. So there will be many tiny grains that will enhance the hardness properties. So addition of nanoparticles here is important as well. Not in terms of a high weightage of amount, but a less weightage of amount as mentioned for the wettability. So even in some cases, we can see that addition of nanoparticles actually tries to reduce the needle shaped zinc. So you can see the needle shaped zinc actually reduces upon addition of nickel nanoparticles, and they are a lot. So when they are a lot, they will try to be another source of strengthening effect. Interfacial properties is actually the part between the solder and the substrate, between the solder and the printed circuit board. This is sort of like a layer that holds the component and also the printed circuit board. So we need a thin layer because thin layer will preserve a good bonding. But when you have a thick layer, the thick layer is prone to crack. So what happens when nanoparticles are added to these lead-free solder alloys? We could see, without and with addition, we could see upon gathering certain literatures, the intermetallic compound layer thickness reduces quite drastically. Okay, I'll tell why. and therefore preserves a thinner IMC layer. So let me just tell you what happens when the nanoparticles are actually at the interfacial layer. So you can see I've separated the solder alloy and the substrate. Diffusion process is highly active at the interface between the maroon or red colored solder and the blue colored substrate. So nanoparticles being as an active element, of course, they will try to slot in at the highest energy area, and at the highest energy area is where the intermetallic layer is formed. So when these nanoparticles are being there, they will block the diffusion process. That means, let's say there is a thing from the solder that tries to merge with the copper in the substrate. Yes, it can, but nanoparticles will actually reduce the diffusion process. Basically, it will not actually produce high rate of diffusion and therefore preserves a thin IMC layer, intermetallic compound layer. But then if there's no nanoparticles, there's freely movement between the solder's element and the substrate. Therefore, at high temperature soldering or even at low temperature soldering, we will produce a higher or thicker intermetallic compound layer. However, again, we need to preserve a less amount of nanoparticles additions. That means if you have high weight percentage, like I said earlier, it will go to the edge of the motion. That means there's still considered as no effect in the center. That means the elements can still move freely without any blocking of the diffusion. So we have to maintain a less amount of weight percentage of addition. I know there might be a question, how do we choose a less amount of weight percentage additions? We can't actually, we have to add certain amount of percentage. For example, we can add 1%, 2%, and 3% in a certain solder alloy. Then we can find out which percentage is giving a good properties. We don't have a standard. That's why this is actually a development of a solder alloy. So we can also see in terms of mechanical properties, additions of nanoparticles increases the hardness. But then if you have to say adding a lot of weight percentage of a nanoparticles, we will have a decrease in the hardness. This is because, again, not because of non-refinement process in terms of the microstructure. Likewise, for the shear strength, we try to add more percentage of nanoparticles. If you have less amount of weight percentage, it gives us more or better shear strength compared to a higher amount of weight percentage addition. This is again due to the agglomeration and also the non-refinement of the microstructure and also the non-refinement of the thin IMC layer. So these are few gathered mechanism that said to be the purpose or the objective for the increase in the shear strength and also hardness. We can see that one of it is grain size refinement, or otherwise called as a Oro-1 strengthening. This is because the nanoparticles will reduce the grain size, and at the same time they act as another second phase strengthening mechanism. Dispersion strengthening load bearing effect is also related to that particular concept. You can see I've highlighted what are those three related to, and the fourth and the fifth point, pinning of grain boundaries and obstruction of dislocation motion, is the nanoparticles will be allocated along the grain boundary. So when the stress is being imposed, nanoparticles are hard materials. They cannot be penetrated. They have to be looped over. They have to be looped over, or they have to be go around. So when more and more dislocation go around, there are piled up dislocation. So it's more harder for the stress to penetrate. And the last one is suppressing effect of the IMC layer, is actually what I explained earlier. It will actually block the diffusion process between the elements in the solder and also the substrate. Therefore, we can get a thin IMC layer. So what does this whole literature review gives us in terms of a hypothesis is no major effect in the melting temperature. The microstructure is said to be finer, produce better intermetallic compound layer in terms of a thin IMC layer, yields improvement in mechanical properties. We saw the hardness and the shear strength increase. Of course, we are using a lead free, so it maintains grain environment as long as we don't add a nanoparticles, that is a plumbum nanoparticles, right? So it's a grain or it's a lead free solder alloy. So what am I doing now? Of course, literature is just for us to study, and it gives us an information. We need some experimental data, or we need some work to really show that that's what the fact is, or what is happening in terms of the current trend. So basically, this is one part of my postgraduate or PhD results that I've taken, and I want to share here, right? Of course, this is a confidential data, but I didn't put in the real confidential matters. Yeah, I just want to explain what I've gathered. Okay, I've given us graph and so on, right? So no worries, it's just a sharing session. Right, so this is basically what I've done. I've tried to add in molybdenum and zirconia. So you can see MO is molybdenum, ZRO2 is zirconia nanoparticles, SB is SNBI. As I mentioned earlier, it's a low temperature solder alloy. Why I want to choose low temperature solder alloy? Of course, I don't want to be having a higher temperature than the SNBB, which is 183. There might be argument from the industry saying that you are using a solder, but then it's still higher temperature than that SNPB. So I've chosen SNBI. But choosing SNBI gives me another problem, which is the mechanical properties. Mechanical properties of SNBI is not that up to the standard or to the level of the SNPB, simply because low melting temperature. So low melting temperature, we know that the diffusion process is not as active or as vast as the high melting point solder alloy. So the intermetallic layer is not that strong. So that is why I try to add in molybdenum and zirconia. Why again molybdenum is a transition metal and zirconia is an oxide metal? I want to see what are the effect on the nanoparticles on a different phase by themselves, because molybdenum is a transition metal, zirconia is an oxide metal, right? This is what other researchers have done also. They have used two different methods, and we see what does it happen. So this is my process. I've weighted it accordingly. I've used 1%, 2%, and 3%. Like I said, we don't have a standard. I can't say 2% will be the best. I can't say 3% will be the worst. I have to investigate. So I've used 1%, 2%, and 3% for both nanoparticles, and they were melted together in a furnace. So we can see that this is the temperature profile. At 600 degrees Celsius, all these materials will be added. And it's thin bismuth molybdenum separately of 1, 2, and 3%, and also thin bismuth zirconia 1%, 2%, 3% separately will be added at 600 degrees Celsius. So then we let it to cool. Once then we will have the solder alloy already. Of course, it is important for me to check if the nanoparticles are there. Like I said, I can't prevail every of the studies, but I did use the elemental X-ray diffraction that actually showed the presence of the zirconia and molybdenum in my solder alloy mixing. So the experiment has passed the first stage of proving that the nanoparticles are in the solder alloy, because if not, there's no point of me adding nanoparticles, but I can't find a nanoparticle inside. So after that, I have to go through a remelting process. This is just to make sure that the nanoparticles are properly mixed. Then I go through a compression to make sure it's smaller in size. Why smaller in size? Go back again, it's because trend towards miniaturization. I don't want to be using a high mass or high dense solder. So the solder alloy will be manufactured or will be punched into in terms of a billet of size 5 mm, right? Because these 5 mm billets, you can see the descriptions below. I've mentioned SB plus MO is basically SNBI plus molybdenum nanoparticles of 1, 2, and 3% separately. Correspondingly, likewise for the zirconia addition, 5 mm will be used for the experimental testing. So what are the experimental testing that I've done is wettability. So what I'll be looking into wettability is upon soldering at 230 degrees Celsius. Why I choose 230 degrees Celsius? It is the recommended soldering temperature in the industry. So I don't want to use another temperature and say at this particular temperature is good. I might just use what is being recommended, and we can see the result directly. So at 230 degrees, it will be soldered at 60 seconds. That means 1 minute. So then I will actually check on the contact angle. We have a special microscope that is embedded with the software that I can measure the contact angle, and then I also have to calculate the spreading area and spreading ratio. Of course, the microstructure involves the SEM and EDX together with the XRD. These are to detect whether the nanoparticles are present at the structure, At the same time, what is happening at the intermetallic layer? So I can see what happens when the nanoparticles are added and what happens when there is no additions. For hardness, I'll be using Vickers hardness because for alloys, they are considered soft metals. So I can't be using the higher hardness machine. Vickers hardness is the recommended. So I've actually imposed 1 kilogram force load at 15 seconds to get the hardness. As for the shear strength, I'm actually using the ASTM standard D1002. That is the standard for soft alloys, solder alloys, soft metals. That are the standard testing methods. So I actually soldered it again at 230 degrees because we want to see what is the relationship. We can't be using a different temperature for the wetting and also the soldering, of course. So I'll be using 230 degrees Celsius. This is to accommodate the shear strength. We'll be using universal tensile machine to pull the specimen. This is called a single shear lap joint. So you can see that the the substrates are overlapping each other, right? You can see basically in the figure C. So what happens when I test it in terms of wettability? A contact angle, as I mentioned earlier, is the angle between the solder and substrate. Spreading area is the wetted area, the area of the wetting or the soldering that took place. So we are actually going towards a lower contact angle, larger spreading area and larger spreading ratio, right? So upon my additions of nanoparticles, I have gathered few data. Okay, we can see that upon additions of molybdenum, all 3% had lower contact angle than the non-added, with the lowest is for the 3%, right? And for zirconia, we also found out that the lowest contact angle is for the 2%, whereas in all other 3%, it is still lower than the SNBB solder alloy, sorry, SNBI solder alloy. So we can say that nanoparticles here has reduced the contact angle and also increased the spreading area. It's very important here to note that the nanoparticles did not actually increase the contact angle. So we could say that our additions here is still acceptable, because if you are producing a high contact angle, that means I still need to reduce maybe less than 1%. Maybe I need to use 0.5, 0.3 and those kind of figures. But looking at it, 1, 2 and 3% is actually producing a lower contact angle. So we can actually proceed with the other testing as well. And again, as I mentioned, spreading area was larger in the nanoparticles added solder for both molybdenum and zirconia. But in both cases, we can see zirconia had a better result. Okay, because probably it's because of a oxide element. I'll explain this later. So we can see that again, yeah. So I have illustrated the model of myself. This is my own model that I've illustrated. What happens when we have the zirconia and molybdenum? In my particular study, the zirconia nanoparticles is much more smaller compared to the molybdenum nanoparticles. So smaller nanoparticles is actually having better segregation properties. So they are evenly or more properly distributed. So the smaller contact angle is produced. Whereas for larger molybdenum, they tend to have van der Waals force that attracts the nanoparticles together. So the process of reducing the contact angle is not much efficient as the zirconia. So that is the reason of this. I found out some agglomeration in the microstructural properties. Right. So earlier I've mentioned that the microstructural properties seem like a subjective area. How do we know if it's grain being reduced in size? So what I've taken here, since our solder is thin and bismuth, I've taken the bismuth area, because from a EDX analysis, I can separate or I can distinguish the difference between the S and thin and also the bismuth area. So I've taken the bismuth area to be calculated. So if I can see if there is a less amount of area calculation for the bismuth, then I can actually relate it with the nanoparticles additions. So what I'm doing here, I'll actually be measuring the area of the bismuth. So upon additions of nanoparticles, this is the measurement that I took. I mean, we have a software that can actually calculate the area for us. We have to of course separate the area of bismuth and tin, but then after the separation is done by me, there's a software that can actually give us the area of the bismuth. I have, of course, have to do it few times to get a proper average, and then we can say that this is a consistent results. So we can see the first one is for the non-added. Then accordingly, I've listed the additions of nanoparticles in the increasing percentage. Looking at the zirconia, let's look at the zirconia first. All 3% of additions had lesser or had given us a measurement of the BI area which is lower than the SNBI. Whereas for the molybdenum addition, the 2% only had a higher BI measurement, bismuth area measurement compared to the SNBI. There is a reason behind this. Okay, there's a reason behind this that is related to the shear strength or intermetallic compound. Because here, upon study on the microstructure, I have seen less amount of molybdenum are at the solder side. Most of the molybdenum for the 2% has attracted themselves at the interfacial layer. So supposedly when they are being at the interfacial layer, they had to produce thinner IMC layer, which was compatible in this study. So from that, I could actually prove my hypothesis that the nanoparticles, especially for the 2%, molybdenum was not much found in the microstructure or the solder side to reduce the BI area, but was mostly found in the interfacial side that reduces the IMC thickness. However, although this gives a good impression on the IMC thickness layer, but then the hardness properties will not be as good as the shear strength. We need to have a satisfying in terms of both shear strength and also hardness. But we can see that the zirconia here had a lower BI area. So this is simply because of the small size of zirconia nanoparticles. So this is again a model that I've developed. We can see that when you have a larger particles, you can see in picture E, this is actually SEM. I mean, this is not the SEM image. I've extracted and drawn this model from the SEM image. So I know what happened at the particular sites of the BI and also SN. So I've labeled here the BI is actually the dark area. Sorry, the SN is actually a dark area. The BI is the white area. So upon addition of nanoparticles, the reduction basically due to the nanoparticles of zirconia and 1% and 3% of molybdenum is because these nanoparticles restrict the growth of the BI. So they actually produce a smaller or refined BI area. But then for the 2% additions, there was agglomeration and also there was not many presence of molybdenum. So there is no refinement process there. This is what I have been explaining. When the nanoparticles are actually smaller in size, they are properly dispersed. But then when they are larger in size, for example, for molybdenum, they should be given a very much focus that they are evenly distributed. Since we are manually distributing the nanoparticles, it's quite hard to actually have a proper distribution. So it's preferably if you are using a manual or mechanical stirring, you have to use a smaller size nanoparticles. Unless if we have an automated or if we have an injection sort of a nanoparticles machine, then we can use a larger size particles. So we can actually put in the particles at a certain area to improve. Of course, it's cost. And now is the interfacial properties. Interfacial properties, this is the interaction. Basically, we need a thin IMC layer. So what happens, you can see the graph here, the blue color actually the non-added solder alloy. Upon addition of 1 and 2% molybdenum, the interfacial layer increased, but 3% the interfacial layer, sorry, the first 2% decreased and the third percent actually increased the thickness. For zirconia, there was an increased trend, but the first 1 and 2% had lower IMC layer than the SNBI, but the third 3% addition had quite a hike. But it could be really satisfying because if you look at the scale here, this is measured in micrometer. That means the highest that could be obtained for the 3% zirconia is still less than 1 micrometer. Other studies have shown that 2 to 3 or 2 to 5 micrometers of IMC layer thickness is enough to give a proper strength. But what we are producing here is actually less than 1 micrometer. So we are actually preserving a very much less in a IMC layer. So again, what happens? I have to model this we can't really see the ICM image because sometimes the ICM image is too technical. So I've come up with a model so that we can clearly see what is happening. For the 1% and 2% zirconia and the 1% and 2% molybdenum, after detection of the nanoparticles from the SEM and XRD, I've seen that they are mostly distributed at the interface. So they actually block the diffusion process. You can see I've highlighted in black border and I've shown what happens. The red one here, the red arrow is the SN atoms and the white arrows is the copper atoms. So they are being blocked by these nanoparticles. So even though there is production of IMC layer, they are not as thick as what is being found in the 3% zirconia and 3% molybdenum. This is simply because 3% of zirconia and 3% of molybdenum has a high weight percentage. So the tendency to agglomeration to happen there is much more compared to the 1 and 2%. Even so being for the molybdenum, because molybdenum is a larger size particle. So looking at that, I've seen and I've saw that the presence of agglomeration at the interfacial layer. Although there is a blocking of diffusion by the non-agglomerated particles, some places that being agglomerated, the diffusion, blocking of diffusion. So this is a brief summary. So you can see that even though 3% of zirconia had and 3% of molybdenum had a higher thickness or measured a larger thickness, it is still less than 1 micrometer. So it maintained a thin IMC layer compared to the other lithographers. Hardness is again, as mentioned, is one of the mechanical properties, is the ability to resist deformation. So here we can see that additions of nanoparticles not really increase the hardness, but even so there was an increase, the increase was less. But it's important to know that the decrease was not high as well, because probably looking at the nanoparticles at the microstructure, they are not much present there. They are more only present at the interfacial layer, because as I said earlier, interfacial layer is where the high energy is. So nanoparticles being active particles, they will of course go and allocate themselves at the interfacial layer. But then some nanoparticles which did not go to the interfacial layer act or be at the solder area only, on the solder side. So they act as the another second phase dispersion strengthening mechanism that increases the hardness. So it was quite obvious for the 1% zirconia and 3% molybdenum. So what actually happens and how does the nanoparticles impede the dislocations or actually restrict the dislocation? We can see here that the red highlighted dot or round here is actually the nanoparticles. Upon load, upon penetration, the load can't break the nanoparticles because they are small in size. At the same time, they are very hard because they are small inside. They have a higher surface area. So the load has to pass over or loop over. So as more and more loops are being formed, the dislocation of the loops increase. So the density increase. Therefore, the increase in the load is needed to break the bond. So this is why, and this is the reason being the nanoparticles at the solder area. Let me go to the, we could say the important part of a solder alloy is the strength or the shear strength of the solder alloy. So we can see here the shear strength is done basically by using a single lap method. 1% and 2% for both cases had a lower shear strength than the SNBI, but it was more evident in the 2% of molybdenum, because 2% of molybdenum, even though the presence of molybdenum is very high at the point, the production of very thin IMC layer could not actually support the stress. Not only that, there was no molybdenum nanoparticles at the interfacial layer. Just to share with you guys, there was no molybdenum nanoparticles. There was compounds of molybdenum. That means the molybdenum has reacted with the SN and produced MOSN. So the nanoparticles was not there to block the diffusion or to actually restrict the shear strength. But interestingly, when we look at the zirconia, in all three zirconia additions, even though there was zirconia that has been diffused or reacted with the tin or copper, but there was still presence of nanoparticles of zirconia itself. So it actually gives another strengthening effect to the shear strength. So this has to be tallied with the thickness as well. So we could say here that the higher percentage of shear strength was observed for the 3% of zirconia. So this is actually a very high, or quite to say more than half of the SNBI. And comparison with other literatures have said that this could actually be at the par or even higher than the other lead-free solder alloy. So of course this is not being proposed to any industry yet, but this is a research that has been given us certain results. Okay, so again a model to point here. Molybdenum nanoparticles are basically large nanoparticles. So they either agglomerated or they don't actually present themselves at the IMC. They might be on top of the IMC layer or very much below towards the copper substrate. That is the second diagram. So there's not much of a shearing restriction done by this type of presence of nanoparticles on top and bottom of the IMC layer. But then we have smaller size nanoparticles, especially for zirconia, and also observed for the 3% molybdenum, even though there was agglomeration of the 3% molybdenum, but they actually present at the IMC layer. So when the shearing is done, they act as another blocking or restriction particles. So that is why this is of course after I get the scanning electron microscope and XRD results, I have come up with this model. So it could say that the zirconia 3% and the molybdenum 3% had the highest strength. So this is the explanation. Basically whatever I've shown here is written in this slide. So maybe perhaps I'll just summarize. So when you have lesser than 1 micrometer IMC layer, it's still capable to withstand high shear stress. But then looking at the 2% molybdenum, it has a very low shear strength because although it is less than 1 micrometer, it's very, very thin. So perhaps it did not help in terms of shearing resistance. At the same time, a proof hypothesis was there was no presence of molybdenum sold nanoparticles. As discrete particles, they were not there. They were actually in terms of a compound. But in zirconia, the zirconia, even though it reacts with this tin and also copper, there was presence of sold or discrete zirconia. That is why we can see the shear strength of the zirconia in all 3% of addition was way, way higher than the molybdenum additions. Okay, just to give another input, I didn't include it in this slide, but I've done a weighted objective method. So people may be or maybe you guys will be having so much of information, but I don't know what to choose. I had 1-3% of molybdenum, I had 1-2% of zirconia. How could I say this particular percentage and this particular nanoparticles is the best? I've done the weighted objective method. I've scaled it down and I've set the average score of the SNBI, the non-added, as the average score, scale from 1 to 5, and I have done the calculations, and from that 2% of zirconia had the highest scoring percentage. So from this research, 2% of zirconia had the better score compared to the other nanoparticles. Of course, future works has to be done to really prove that another sort of nanoparticles will not surpass zirconia, or if it does surpass zirconia, what are the reasons? So going to that will be the future work. So I've been looking into other nanoparticles. I've done molybdenum and zirconia. Even in my previous research, I've added aluminum oxide and also titanium dioxide into SNBI and also the high temperature SNAGCU. It's not here, it was quite some time I've done the research, but my papers are there. So maybe I need to use another nanoparticles so that I have a concrete result or hypothesis that I can provide to the industry or even the area to actually say this is a proper or this is the novel study of this particular research. So of course these are few reference, and these are the publications I've done up to now. Some are already sent. I think 3 of the papers are there, but still under review, so I did not put it here. I just put whatever I've published. So I think this will be the end of my slide. And I really thank everybody for this particular webinar session. I hope I've given enough, or I've given us introduction or results sort of to know what is the current trend in the solder alloy technology. Of course, I furthered with nanoparticles addition because I don't want it to just look at 5 years before kind of studies. I want to be up to date. So with that, I will actually say thank you and end my session here.
Thank you, sir. Dear participants, if you have any queries, kindly post it in the chat box so that the speaker can answer your questions. Sir, your session was very informative. Before you could answer the questions of the participants, I would like to read out a few comments that has been posted in the chat box. The participants have posted it as the session is very informative, it is very influential, and it is an excellent session. And other participants have posted it as nice and wonderful. The session is very useful with very nice PPT presentations.
Thank you. I'm glad to hear that.
Sir, I would like to read out one question to you.
Okay.
What is the maximum shear strength of using solder material?
All right. So can I show my slides?
Yes, of course.
Okay. This is my work, so I really can't. I can't show the results, but I given us the 66% higher. So let me go to the literature review. Maybe we can see few studies that have come up with a certain shear strength measurement. Okay, so let's look at this. This is actually in terms of megapascal. So the highest that we have seen here is 24.86, but we can't have a standard shear strength because it varies in terms of melting temperature, in terms of the additions of nanoparticles and so on. So to answer that, we need to actually compare with the non-added solder alloy itself. For example, here we could see the non-added solder alloy is SNCU 15.1 megapascal. So this researcher has added argentum and he come up with 24.86 as the highest. So what he will do is he will compare, or he or she will compare with other researchers that has been done with the same SNCU. So that's how we can actually gauge our shear strength. So even I have done SNBI, I have to find, or I have to see another researcher that has done SNBI also, and what is the shear strength. So that's how we can actually come up with this particular data, or we could say a result. I hope that answers the questions.
Thank you, sir. There's another question posted here. What about the processing speed of this one?
Yes, sir. This is yes. This is a good question. We must, or if you ask me, we must use a standard procedure so that we are actually following what is happening in the real world. So ASTM D1002 has provided us the speed. So the speed here, I can assure you, it's mentioned here 1.3 millimeter per minute. I didn't come up with this figure. This is according to the ASTM standard. Different standard have a different speed for a different material. Since we are dealing with solder alloys, soft materials, and accordance to this ASTM, we must be using 1.3. And to further give an information, when you are using 1.3, you also have to produce the specimen according to the dimensions. So you can see the dimensions here. Your solder area must be 5 times 10 mm. Different types of standard will have different dimensions.
Thank you, sir. I, on behalf of the participants, thank you for giving a clear answer with PPT reference.
Thank you.
There are no more questions to be read out, sir. So I think we can move on to the vote of thanks session.
Thank you, sir. It's my honor to have been asked to propose a vote of thanks on this occasion. This is Mrs. Shala F. John, Assistant Professor, Department of English, Francis Xavier Engineering College, Tirunelveli. First and foremost, I would like to thank Lord Almighty for His manifold blessings all throughout this webinar. I, on behalf of the management, Department of English and Department of Mechanical Engineering, extend a heartfelt thanks to the delegate of the day, Mr. Amras Singh, Department of Mechanical Engineering, CG University, Malaysia, for sharing his knowledge and expertise on lead-free solder development towards green technology. Sir, your thought towards green technology will indeed provoke the minds of the budding engineers to revolutionize a change in the technological development. I thank you, sir. I extend my sincere thanks to the management, to our beloved principal, Dr. Velmurugan sir, General Manager Development, Dr. Jayakumar sir, Professor Academics, Mrs. L.R. Priya ma'am, for their strenuous support. Also, I would like to place on record a special thanks to Dr. Joe Patrick, HOD, Department of Mechanical Engineering, Francis Xavier Engineering College, and the department faculty members for rendering technical support in conducting this webinar. Thank you all. I owe a deepest sense of gratitude to all the participants of the day, the learned professors and students from various colleges across the nation who made this event successful. Once again, I thank you all.